So Professor Shoichi Fujimori will continue with his lectures on zero mean curvature surface in Lorentz Minkowski space. Today he will talk about non-orientable maximal surfaces with one end in Lorentz Minkowski space.
Thank you very much for the introduction. Today I'm focusing on the non-orientable maximal surface. So my mic is...
It's on.
Yeah.
Your mic?
Yeah.
You need to remove the audio from here.
So yes.
Just go to Zoom here.
Yes.
Here you just click. There was
Yeah.
remove audio from here. Remove audio. In this remove audio. Any option?
MU.
Remove audio.
Audio? Audio is...
Yes, this one. Remove. Yes. No.
Okay. Okay. Thank you.
Then go
Okay.
back to your slide.
Yeah, okay.
Yes. Good.
Okay. Thank you. Okay. So today I'm going to talk about non-orientable maximal surfaces, and especially surfaces with one end in the Lorentz Minkowski 3 space. So, but as I mentioned yesterday, there's no non-orientable surfaces in Lorentz Minkowski 3 space. So, so first, I will recall something, some basic facts about minimal surfaces in Euclidean space. Then I go to the Lorentz case. Now, minimal surfaces in R3. So, since many speakers already introduced, there is a famous wireless representation that is let M a Riemann surface and F a minimal surface, that is a vanishing mean curvature. Then there exists a meromorphic function G and holomorphic one form eta on M such that F can be represented this way. Okay. And the first fundamental form is this. Okay. And we call this pair G and eta the wireless theta of F. And also, this meromorphic function G is actually the composition of the unit normal vector field and the stereographic projection. So this G is called the Gauss map of F. So the Gauss map is meromorphic function. Okay. And so there is a global property of minimal surface. Let M a complete minimal surface of finite total curvature. So this is finite total curvature with the wireless data. And then there exists a compact Riemann surface and finite points in M, so that M is biholomorphic to this compact surface with n points. Okay. And these wireless data defined on M can extend meromorphically to M bar, this compact surface. So in particular, G is extended meromorphically to M bar. So G can be considered as a meromorphic function on M bar. So this means G is a map from compact surface to CP1. So this and holomorphic map. So we can define the mapping degree of G. And the degree of G satisfies this inequality. So this is greater than or equal to minus Euler characteristic of M bar plus 2n. And the equality condition is also known. Okay. And the period problem, so let M a Riemann surface and G a meromorphic function and eta holomorphic one form, so that this gives a complete Riemannian metric of finite total curvature. And when M is not simply connected, then this integral, this path integral, might not be well defined. So the value might depend on the path, okay? So the F is very defined on M, if and only if this is 0, 0, 0 for any loop in M, okay? So now we consider the non-orientable minimal surface. So let M prime a non-orientable surface. We say F prime, a map from M prime to R into R3, a non-orientable minimal surfaces if the mean curvature with respect to a unit normal vanishes identically. So mean curvature depends on the unit normal. So if we take the unit normal other side, then the mean curvature changes, the sign of mean curvature changes. But the modulus of mean curvature define even the surface is non-orientable. So, and the minimal surfaces is surfaces with vanishing mean curvature. So we can define non-orientable minimal surface. Okay. And now let F prime be a complete non-orientable minimal surface of finite total curvature. Then we can take a double cover where M is an orientable surface. And then F is an orientable minimal surface. So we can take double cover, then we have orientable minimal surface. And then, so since then we can take this a Riemann surface, so one can apply the Weierstrass representation. Okay. And let G and eta the Weierstrass data of F. And let I be the anti-holomorphic deck transformation with respect to pi, then we have this. Okay. If P equals the composition of F of I, F and I. And in this case, so if we have this, then G and eta, we have this property. So when F has this property, then G and eta has these properties. Okay? The composition of G and I is minus 1 over G bar. So G gets antipolar point. And the pullback of eta by I is square conjugate of square root G squared eta. So this is so by just compute using this equation. So this is easy computation. Okay. And now we consider the Gauss map of non-orientable minimal surface. Let F prime be a complete non-orientable minimal surface of finite total curvature, and G the Gauss map of double cover. Yeah. So then G is a meromorphic function, and take I the anti-holomorphic deck transformation with respect to pi. Then there exists G hat, which is a map from M prime into projective plane, real projective plane, such that the following diagram is commutative. So now, so this is pi double cover, and this G hat, and G, and this P naught is standard double cover from natural projection from CP1 to RP2. So identify with antipolar points. So in this way, we can get G hat, which is mapped from non-orientable surface into RP2. So then we call this G hat the Gauss map of a non-orientable minimal surface, F hat. Okay, and since this is degree 2, and this is also degree 2, So we can define the degree, mapping degree of this G hat, such as this as degree of G. So we can define degree of G hat. Okay. Now, this degree of G hat, we have a property which is proved by Mix about 40 years ago. Let F prime be a complete non-orientable minimal surface of finite total curvature, and G hat the Gauss map of F prime. Then the degree of G hat is congruent to the Euler characteristic of the compactification of M prime mod 2. So, okay, so here if M prime bar is RP2, then degree of G is odd. Okay? So if the compactification of M prime is Klein-Bottle, then this is always even number, okay? And so on. So this is quite a strong result, but so to show this theorem, Mix showed this lemma. So let M1, Mj be compact to manifold such that with empty boundary, so without boundary. Okay, and P from M1 to M2 are branched covering. Then Mix showed that if the Euler characteristic of M2 is even, then this is also even. Okay, so the Euler characteristic this is even, then this is covering, so this is also even. Okay. And if this is odd, so Euler characteristic of M2 is odd, then the Euler characteristic of M1 and the degree of P are congruent mod 2. Okay. So if P is not branched covering, then it is obvious. But Mix showed that even this is branched covering, it holds. So now if we can prove this, so we need only this part, the second part. So in this case, the Gauss map is a map from M bar prime to RP2. So this is the Euler characteristic of this is 1. So this M2. So this is G Gauss map. This is RP2. So we have this. So this is the result. Okay. So we have this property for minimal surfaces. Okay. And as a corollary, Mix showed that let F prime be a complete non-orientable minimal surface of finite total curvature and G the Gauss map of F prime, then the degree of G hat is greater than or equal to 3. Okay. So the proof is as follows. So let M pi be the double cover. Then degree is 1, then M is this. So, and by applying the Osama inequality, it should have embedded ends. So then we can say M is catenoid. And degree equal 2, then M should be, the double cover should be torus minus 2 point and the embedded end. So it should be the genus 1 catenoid, but it's known that genus 1 catenoid does not exist as a minimal surface. So we have no genus 1 example, degree 1 example, degree 2 example. So we have degree 3, at least degree 3. Okay. And then Mix also have the following. Here's this example, the Mabel strip. So let M, the double cover, is a C minus 0. So this is CP1 minus 2 points. And then I define the antipodal point map, antipodal map. Then M prime M over this I. So this is RP2 minus 1 point. And he defined G and eta this way. Then, yeah, this is, he compute the residue at the end. Then he could show that this is well defined. And we have Möbius strip. Okay. So this is, yeah, also a subfield model of Möbius strip. And so also, so this is an example of minimal surface of non-orientable minimal surface of degree G equal to 3. So degree G is at least 3. So this is one of the simplest example. And also it is shown that this is a unique example of this degree. So degree 3 is only, we have only this example. And but yeah, so for if, and in this topology, the degree of Gauss map is always odd. So now next simple case is degree 5. So then degree 5 case, there are many examples. But the degree 3, so this is only the example. So this is the non-orientable minimal surface. And then later, in 1990s, Francisco Lopez constructed a Klein bottle, one-ended Klein bottle. So in this case, degree of Gauss map is even number. So the simplest case is degree 4. And the double cover is a torus, this algebraic curve, elliptic curve, and remove 2 points. Then after the projection, we have the Klein bottle minus 1 point. Okay? And then he set the wireless data this way. Yes, so here we have one parameter here, R. Then he could show there exists unique R so that this gives a well-defined minimal surface. Okay. So in the proof, yesterday I gave some explicit construction of maximal surface. The method is pretty similar, but finally, in this case, by using symmetry of the surface, he reduced the period problem for one equation, one real equation with one parameter R. And then he showed that the graph of such a polynomial is like this, so monotonically increasing. And when R goes to minus infinity, this value is negative, and the R goes to plus infinity, this value is positive. So there exists a unique solution. So this is his method to proving the existence. Okay. And later, so maybe this example is published in 1993, then later he showed that the uniqueness of the surface. So non-orientable surface with degree 4, this is only this example. So this is Klein bottle minus 1 point. Okay. And later, Lopez and Martin, Francisco Lopez and Francisco Martin, succeed to generalize a genus. So they could create a higher genus example. So for each K, so then the double cover of Riemann surface of this, and this is Riemann surface of genus K. And then we set I, the Dick transformation, and G and eta this way. And they could solve the again, there is unique R for each K, there exists unique R, which depends on K, such that the period problem is solved, okay? But the graphics, so since the degree is pretty high, and the surface looks very, very complicated, so the K equal 2 case already very complicated, some K equal 3 case. But in each case, they use the symmetry and reduce the period problem so that period problem to be one equation for one variable. So they said in this case they reduce this equation. So they solve that there exists unique R so that this equation holds. Okay. So and each R, so they still have this kind of graph for this left-hand side. Left-hand side is, so we have many variables, K, R, T, but K is positive and fixed, each K, and T is integrated. So after integration, there is only, this is a function of R. And so each K, we have a similar graph, yeah? And if we change K, the graph bit slightly shifted, but always monotonically increasing. So we can always say that there's a unique solution. So this is minimal surface case, okay? So later we think about the maximal surface case and the graph is very different. Okay, so in this case, we always have monotonically increasing graph. So we can say always a unique solution. Okay. So this is minimal surface. So in this way, they produce higher genus non-orientable minimal surfaces. It is in 1990s. And now we switch to the maximal surface case. And as I introduced yesterday, so let L3 be the Lorentz Minkowski 3 space, and the inner product is this. So this is indefinite inner product, but non-degenerate, symmetric, bilinear form. And let M be a two-dimensional manifold, and F is called space-like if the tangent vector is positive definite. Yes, okay. Tangent vector is space-like. So the tangent plane, the induced metric to the tangent plane is positive definite. And we call the surface is maximal surface if it is space-like surface with mean curvature, zero vanishing mean curvature. And as I mentioned yesterday again, we have Kobayashi's representation like wire-thrust representation. So let M a Riemann surface and F a maximal surface. Then there exists a meromorphic function G and a holomorphic one form eta such that F can be described this way. Okay. So minimal surface case, here is minus and here is plus. So only a small change. And then in this case, we have minus here. And so the G and the eta are called the wire-source data of F, and G is now called stereographic composition of the unit normal vector field and stereographic projection. But the Gauss map unit normal vector field takes value at H2, not S2. So the stereographic projection is from H2 to disk, the upper half of H2 to disk, or lower half of hyperbolic plane to outside of disk. So anyway, we have G is, we can say G is the Gauss map of F. And also I mentioned yesterday, if maximal surface is complete, then it must be a plane. And there does not exist no orientable space-like surface without singularity. So now we consider the maximal surface with the singularities. So yeah, this is also mentioned before yesterday, but this is if F is called max space if there exists open dense subset W such that the restriction to the W is conformal maximal in motion, and the differential of F is non-zero. So rank can be, so if the point P, F is in motion at point P, the rank of dF is 2. But so at the singularity, rank is less than 2, but we assume that rank is at least 1. So we don't allow the rank 0 point. So in this case, so this is always positive definite. So the maximal surface, this might be degenerate, might degenerate. So here minus might degenerate. But this is always positive definite. And the set of singular point is, so the zeros of eta we don't allow. So the singular set is exactly the point here. The modulus of g equal to 1. And then the max phase is complete if there exists a compact set C and symmetric 2 tensor T such that T is 0 on M minus C and ds plus T is a complete Riemannian metric. So we can somehow deform so that only a compact area we can deform so that we can make a complete Riemannian metric. And then also we have Osman type inequality. So let F a complete max phase and G eta the wire source data. Then there exists. So now we don't need any assumption of finite total curvature. Then again we have compact Riemann surface M bar and finite many points, such that M is biholomorphic to M bar minus these finite points. And these wire source data, G and eta, extend meromorphically to M bar, this compact Riemann surface. And these points corresponds to the end of the surface. So we don't have a compact maximal surface, compact max phase. Yes. And then, so let F a complete max phase, then yeah, we can put M as a compact surface minus n points. And let G and eta as a wire source data. Then we again have the same inequality. 2 times degree G is greater than or equal to minus Euler characteristic of M bar plus 2n. And the equality holds if and only if each end is properly embedded. So surface might have self-intersection, but each end is embedded. So this is a general setting. Okay, now we go non-orientable max phase from now. So let M prime a non-orientable surface. And a map F prime from M prime into L3 is called non-orientable max phase if there exists a Riemann surface M and a double cover such that this F is a max phase. So if we can take double cover so that the double cover is max phase, then we can say this is non-orientable max phase. And also, completeness is also defined this way. F prime is complete if this double cover is complete. Okay. And let G and eta, the wire source data of F, and I, the anti-holomorphic order 2 deck transformation associated to pi. Then we have this again. So yeah, double cover. So since M is double cover, so F and a composition of F and I goes to the same point. Okay. And in this setting, the y-source data changes this way. The composition of G and I is 1 over G bar. So minimal surface case 1 over minus G bar, but now just 1 over G bar. Okay. So not the antipodal point. And the pullback of eta by I is now a conjugate of G squared eta. So this is again, we don't have minus here. Okay. Now, we'd like to define the Gauss map of non-orientable max phase. So let F prime a non-orientable max phase. So then we have, there exists M, double cover, and we take pi, the double cover, and G, the Gauss map of this double cover. And we define the map A as follows. AZ is equal to 1 over Z bar. So not antipodal point, but so symmetric with respect to the equator. Okay. So the unit circle invariant by this A. And we define P naught, the projection from the CP1 to this. Then there exists unique conformal map, G hat, such that this holds, this commute. So here we have double cover. So also here we also kind of double cover. So but the unit circle is not defined. But then, so yeah, remember that the singular set of F is equal to 1. So except singularity, so it doesn't take value this. So we have some G hat take values here. And there exists unique G hat here. So we call this G hat the Gauss map of F prime. Okay. And again, we can define the degree of this Gauss map, G hat, equal to the degree of G. Okay. So this is a Gauss map. So this is not RP2 anymore, but this funny things. Yeah. And now consider the degree of the Gauss map. In minimal surface case, a degree of the Gauss map is congruent to the Euler characteristic of M prime bar mod 2. But in this case, we have this theorem. Let F prime a complete non-orientable max phase and G hat the Gauss map of F prime. Then degree of G hat is always even. So not congruent to the non-orientable surface mod 2. So always even. And cannot be 2. So greater than 2. So at least 4. So the degree of Gauss map is 4, 6, 8, 10, and so on. Okay. So this is a quite different result compared to minimal surface case. And to prove this, we use this lemma. This is proved by Ross in 1992. Let M bar is Marty Ross. Yeah. Yeah, when I work about this non-oriental max phase, I stayed Granada University Spain for about 1 or 2 months and work and talk to Francisco Lopez every day. And one day, Professor Lopez told me this theorem. So the other day, Lopez is not at the university. He has something. So I stayed at the university alone. Then I want to know the proof. So then Lopez said, this is a theorem by Ross. So I thought this was Antonio Ross. Antonio Ross was the professor at Granada University. So then I knocked him. Then I asked this theorem, but then Antonio Ross said, this is not me. But he said that he knows the proof. So he told me. So yeah, so this is not the different Ross. This Ross, Marty Ross is maybe Australia. So anyway, the lemma that let M bar a compact Riemann surface and I anti-holomorphic involution without a fixed point. Then there exists a function h such that the composition of h and I is minus 1 over h bar. Okay. So we apply this lemma to prove this theorem. So first, in this setting, we have I, this I. So by using the lemma of Ross, we have this H. And this is the Gauss map of the double cover of Mach space. And so that, and if one finds this H, then we can slightly modify the H by using Möbius transformation so that any zero and poles are not zero and poles of G. So we can assume that G and H has no common zero, no common common poles. I mean, so and we set capital G as follows, the multiplication. So then we can say degree of this capital G is degree of small g plus degree of small h. And now consider the composition of capital G and I. Then this G is GH. And from this, we have this equation. And this G, we already show that this changed to this 1 over G bar. And by Ross theorem, this holds. So as a result, we have this. So capital G, composition of capital G and I is minus 1 over G bar. Okay. So then Meek's lemma, as I introduced before, is that this the Euler characteristic of M prime bar congruent to degree of G mod 2. Also, yes. So also H has this property. So also the Euler characteristic of M prime bar is congruent to degree of H mod 2. So, and this, we have this holds. Then, so on the degree of G, yes, this is congruent to this mod 2, and degree of G is also congruent to mod 2. So degree of H is congruent to degree of H plus degree of G. Okay. Mod 2. Hence, this should be even. Is it okay? And so we now prove that we have proven degree of G is even. And it is easy to show that there does not exist degree 2 example. This is not difficult. So we say that degree of G hat is even and greater than 2. Okay. So now, minimal surface case, the degree of the Gauss map for Möbius strip is odd number, but in this case, degree is always even. So the simplest example is degree G equal to 4. So in this case, we have two cases, so that one is G is branched at the end, and the other is G is not branched at the end. So the minimal surface case, we only have this case. And the mix showed there's a unique example with degree 3. But in this case, degree 4, we have these two cases. And this case, if G is branched at the end, this is a unique example. It is easy to prove. On the other hand, if G is not branched at the end, we have this kind of example, non-orientable maximal surface. But in this case, we have 2-parameter family. So this is not unique. So we have moduli space 2-parameter family. Okay. So let me show the wireless data. So M is this, and I is this. And when the Gauss map branched at the end, so we have the wireless data this way. And when the Gauss map is not branched at the end, then we have this wireless data. So here we have 3 parameters, R, S, and T. R is positive real, and ST complex. So we have real 5-dimensional, but R and S and T satisfy 3 equations. So 3 real equations. So finally, we have 2-parameter family of the surface. Okay. So this is minimal maximal Möbius strip, non-orientable maximal Möbius strip. And also, in this case, we have, so degree is 4. We can construct 2-ended projective plane. So we can have one more puncture from Möbius strip. In this case, the double cover has Riemann sphere minus 4 points. And in this case, we have many cases. But finally, we have this wireless representation, wireless data. And so my student Kaneda shows that there exists unique example of this topology. So 2-ended projected plane with degree G equal to 4. So then the value numerically value is this. But this is a solution of some complicated polynomial of degree 24 or something like that. So very long polynomials. And we first found 8 examples, but finally, by using symmetry of the surface, we reduce this surface same, this surface and congruent, and so on. So finally, we can say that this is unique. So, and in this surface, this is one end. It looks like catenoid ends. This is embedded end. And on the other hand, the other end is like very complicated behavior. So go down and go up and go down, go up. It's very like n-path surfaces. So anyway, this is unique example with this topology. Also, we have one-ended Klein bottle with degree G hat equal to 4. So minimal surface case, Professor Lopez showed there is a unique Klein bottle, one-ended Klein bottle with degree G equal to 4. So, but in this case, we could prove that one-ended Klein bottle, we have two Klein bottles. So this one is this one. So two different Klein bottles. And after assuming that some certain symmetry, then we can show that the max phase one-ended Klein bottle with degree G equal to 4 must be one of these. So we have only two solutions. Okay. Yeah, the wire source data is here. So the double cover is torus with parameter, one parameter R. And we can set the wire source data this way. And again, we can reduce the period problem for one equation with one parameter. But in the minimal surface case, the graph is like monotonically increasing. So it is quite easy to show there exists two unique solutions. But in this case, we have this kind of graph. So yeah, so now we see there are two equations, two solutions. But so it is quite hard to sort of prove there are only two, and there is two solutions. So okay, yeah, sorry. So the minimal surface case, yes. So we have this kind of equation. So we can say this has always unique solution. So, but yeah, in this case, so the first derivative is always positive, and if R goes to minus infinity, negative, goes plus infinity, it's positive. So it is quite easy, not easy, but compared to maximal surface case, quite easy. But we have a similar equation, but the behavior is quite different. Yes. So, but yeah, anyway, we could prove that we have two solutions. And then I tried to, after we published this is published in 2010, so 14 years ago. And then after that, I tried to generalize. But so compared to minimal surface, in this case, degree is always even. So minimal surface case, degree is even, odd, switched, yeah, depending on the genus. But in this case, so we have always even number of degrees. So it is hard to generalize, how to generalize. So I tried to several ways, but in this case, some case, so if k equal 1, we have this two solutions, k equal 2, k equal 3, then k equal 4, finally we don't have solution, something like that. So we cannot prove the generalized genus, but my student Kaneda success to generalize. So higher genus one. So in this case, so minimal surface case, the degree is 3k plus 1 or something like that. So degree changed odd, even, odd, even. But in this case, degree is 2 times k plus 1. So it is this is always even. And the Riemann surface, the double cover is defined this way with one parameter R. And we can set I, G, eta this way. Then we could prove that for each k, so this is a genus of double cover. For each case, there exists exactly 2 R, for which the max space is well defined. Okay, so the graph changes slightly. This is k equal 2, k equal 3, k equal 4. Slightly changes, but always to have 2 solutions. Okay, and also if we put k equal 1, the surface is exactly the same as the surface we constructed 14 years ago. Okay. So this is one of our theorem. So I'd like to go on to proof, to give a brief outline of proof. Okay, now the Riemann surface is defined this way. The double cover. Double cover is this gives a Riemann surface of genus K and remove 2 points. And I and G and eta are set this way. So the divisor of G and eta and so on is this. So this means the 0 of order 1. This is pole of order K. This is pole of order K plus 1. This is 0 of order 2 or something like that. Okay. So here, so by this Riemann surface, this point, this point, this point, these 4 points are branch points. So only 1 point. But these one is z equal minus 1, z equal 1 is not branch point. So we have k plus 1 points here, k plus 1 points here. So G is here k plus 1 simple zeros. And k plus 1 simple pole. And this is simple pole and pole of order k, simple zero, and 0 of order k. So we have k plus 1, 0, 1, 0, k 0. So degree is 2k plus 2. And here, so this point is just a normal point. So because eta is not, eta is a regular point. So this is minus 1 is also, because this squared eta is a regular point. So this is the regular point of the surface. And this part, yeah, so G has order pole of order k, but eta has 0 of order 2k. So this cancel, so that this is also normal point. So this is also. And here, everything has pole. So and this is the end of the surface. This is also the end of the surface. So the double cover has 2 ends. And after the projection, this goes to the same point. So the non-orientable surface has 1 end. Okay. Now, consider the symmetry of the surface to reduce the period problem. So the similar way to the yesterday's talk, we define the conformal map kappa j, kappa 1, kappa 2 as follows. So this is just involution, and this is, so z do not change, but w changed. Okay. So the next sheet, so kappa 1 p is the same point, but next sheet, okay. Then we have the following. So the pullback of phi is this, okay? And pullback of phi by kappa 1 is k1 times phi, so, and the k1 is this O3 matrix. Also, the pullback of phi by kappa 2 is k2 times phi bar, so and the k2 is this. So, so this symmetry, and we set two gamma 1s. This is one sheet of z-plane, projection of z-plane of the Riemann surface. So this gamma 1 and gamma 2 is quite complicated, this, right? So then, so gamma L, gamma 1, gamma 2, and multiplied by kappa j several times contains a homology base of M bar. And since we know this property, so we only consider the loop gamma 1 and gamma 2. So we only consider the gamma 1, gamma 2, and phi j is this. Okay, this is phi 1, phi 2, phi 3. So 3 components and 2 loops. So we have 6 equations here. Now, so period problem is reduced to 6 equations. Okay, but again, the third component can be written this way. So this is the exact form. So the third component is always 0, integration, after integration, for any gamma. So period problem is now 6 equations, but so we have this. So now we don't need to consider this case. So we only need to consider j equal 1, 2, L equal 1, 2, so 4 equations now. And direct computation, no. Yeah. Also, integral of phi j with respect to gamma, this equals to this. This is in general holds. And the property of I, this is just conjugate, compressed conjugate. So we only need the real part to be 0. So by this equation, we can set period problem, we can reduce period problem this way. Okay. So now we no need real part, but here we have this. And also, by straightforward calculation shows that I star of gamma 1 is gamma 1. And also I star is this way. So, okay, so L equal 1 case, if we set L equal 1, then here 2 times L1. So this equal to 0 is just this equal to 0. And so we have this. And also, this case, L equal 2 case, so here we have minus gamma 2. So gamma 1 minus gamma 2, so cancels, and gamma 1 plus something gamma 1. So, and by using the previous result, so this solves if and only if, so gamma 1 equal solves. So we have this. Now we have 2 equations. We can reduce 2 equations. Okay. And now, phi 1 is 1 plus d squared times eta, and phi 2 is equal to I times 1 minus d squared times eta. So, so we have this, we want these equations. So, and here we have plus and minus. So the period problem is now this. Okay? So the integration of eta around gamma 1 and the integration of g square eta by gamma 1 equal to 0. Okay? So 2 complex equations. And now, and so we have this holds, gamma 1 eta is I star gamma 1, I star eta. And I mentioned before, this becomes a conjugate of g squared eta. So if it is 0, then this is automatically 0, yeah, by this relation. So the period problem is one of these equation holds. So if one holds, then the other holds automatically. So we can say the period problem is now this equation. Okay. So one complex equation. But then the gamma 1, yes, gamma 1 is here. So gamma 1 is surrounded R and minus 1 over R. So we again want gamma 1 to collapse to the real axis, this and this, this and this. Okay. Then we can evaluate the integration. But, okay, so you can see the period from here. So we have z cubed in the denominator. So it has pole at z equal to 0. So we cannot directly collapse the path to the real line segment. But then again, we add some exact one form. So, so we set big F this way. This is very complicated. It is quite hard to find out such a F, but finally we can find. Then the derivative of this and add this. So this is exact form, of course. Then we have this, where A is this polynomial of R. And now, this is holomorphic. So then we can reduce the period problem to the path to, we can collapse path to the real axis. Okay. And F is very defined on M if and only if. So this part, okay, so this goes to 0. So if we consider take integral from this way and this way, so we have 2 times of this. So we can, if we say this equal to 0, then period problem is solved. Okay. So we consider this. Now, so the term here we have 1 minus 1 over R, so it is not difficult. It is difficult to evaluate. So we change the variable t equal minus rz. Then we can rewrite c this way. So the integral from 0 to 1 and here. Okay. So we want to show this has exactly two solutions. Okay. First of all, if R goes to minus infinity, yes, and also we can say this C defined R minus 0 to R. So we already removed R 0, 1. So R cannot be 0, cannot be 1. So as a setting, in the setting of maximal surface. But so this psi can be defined for R equal 1 case. And we can easily show that the limit R goes to minus infinity, this psi minus is negative. And R goes to plus infinity, again psi is negative. And R goes to 0, then psi goes minus infinity. Okay. So yes. And then we can show that for each k, psi of k over k plus 1 is positive. Okay. And psi of 1 is negative. So the graph looks like or something like that. Yeah. So here 1, 0. So graph looks like this. So we expect, but now we don't know here. Here we might have solutions here, or here we might have several solutions. At least we know this is negative, and this is negative, and here we have plus, positive. So we now know C has at least two roots between 0 and 1. Okay. So, but actually, by computing psi prime and psi double prime near the root of the psi, we see that psi has exactly two real roots. Where I don't know. Yeah. So I will explain this later if I have time, more detail. So anyway, so if we prove this, then we see that for each k, for each positive integer, we have two solutions. Okay, so the k equal 2k is, this is two one-ended non-orientable surface, and the double covers genus 2. So I don't know how to see the picture, but anyway, we have two solutions, and k equals 3k. So on the Mathematica, we can compute by Mathematica the numerical value of R, two values. So always between 0 and 1, we have two solutions. Okay. And also the singularity. In this talk, I didn't mention about the singularity, but we can apply the criteria for the singularity by using wireless data. Singularity for this is a picture of k equal 2 case. So we identify the surface. We have k plus 1 copy of Z plane. And since this is non-orientable, we only need to consider the inside the unit disk for each copy. So on each copy, we have this singular set here and here, two components. And by numerical computation, this triangle indicates swallowtail. So we have 4 swallowtails here. And this circle indicates a cuspidal cross cap. So we have 5 cuspidal cross cap. And the other singularity is cuspidal edge. And in this case, k equal 2, so we have 3 copies of them. So actually, in the whole entire surface, we have 12 swallowtails, 4 times 3. And here we have 5 cuspidal cross caps. So totally, we have 15 cuspidal cross cap. And the other singularity is cuspidal edge. So if k increase, then this is multiple to, so swallowtail, total number of swallowtails is 4 times k plus 4 times k plus 1. K plus 1 times 4. And the cuspidal cross cap is 5 times k plus 1. But this is numerical result. And also, I still have, yeah, okay. So that's all about my talk, but maybe remaining time. Okay, let me explain here this part. So we already know that psi has at least 2 roots in 0 and 1, between 0 and 1. But really exactly we have exactly 2 roots. Okay. So to prove this, first if R naught satisfy, R naught is a root of psi. Then there exists R naught minus. So thus R naught, the root must be a positive. Okay, so we can show this. And R naught minus can be written down explicitly depending on K. K plus 2 minus. Yeah, something like that. This is quite complicated. Anyway, so we can. So by this, we can see that the phi has no root in the negative value R. Okay. And also, we can show, so if R naught is a root, satisfies R naught equals 0, then the derivative of psi can be written this way at R naught. K plus 2 R naught minus 1, 3, Q1 R naught. Something like that. Double prime is now K plus 2 R naught 2 K plus 1 Q2 R0 plus 1. And where A naught R naught is quite complicated, but anyway some positive number. And also Q1R and Q2R are polynomial of degree 4. So it's quite long, so I don't write down explicitly, but yeah, anyway, degree 4 polynomials. Okay, so if Q1 is positive, Q1 R naught is positive, then this is positive, and this is negative, then this is negative. Okay, this is 0, then this is 0. So also in this double prime case, Q2, so the remaining part is always positive. So these are positive. So if Q2 is positive, then this is positive. This is negative, this is negative. This is 0, this is 0. Okay. And now we can say Q1, now we focus this Q1. Okay. So Q1, double prime R is always negative. And also Q1 0 is negative, Q1 R naught minus. R naught minus is this value, this non-negative value. 0 and Q of K plus 1, K is negative. Okay, so this is complicated. But anyway, then we have, so Q1 looks like this. So double prime is always negative. So and R naught minus k over k plus 1 here. So there exists unique solution here between here there's unique solution here and unique solution here as well. So we call this S0 and S1. Okay. And thus, yes, so unique S0 R and S minus. Unique S1. After that, Q1 S0 equal to Q1 S1 equal to Z. Okay. So Q1 is this. So this means Q1 is the sign of Q1 is related to the sign of phi prime, of psi prime. Okay, so yes, Q1 is here. Okay, sign the same, always same. So for if the root of psi is here, then psi r is positive. So this means that psi is something like that. R naught is here, and S1 is here, and R naught minus is here. So psi looks like this. Okay, this is psi r. So thus psi of r has at most one root in S1. Okay? No. At most one root in here R naught minus to S1. Okay? So in this setting, psi has at most one root. Okay? And then, okay, so let me copy this. And now, the case R naught is greater than S1, then this psi naught at psi prime of at R naught is negative. So then the surface graph looks like this, yeah, psi r. So somewhere S1 here and R naught here. So thus the psi of R has at most one root in S1 infinity. Okay. And also we see that Q2, which is related to double prime, psi of double prime, S1 is negative. So this means double prime at S1 is negative. So now, if R naught, the root of psi, is in here, then this is increasing solution. So this R naught is here, then is decreasing. But so we don't think about the case R naught is equal to S1. Yeah? So this is less than S1, this is bigger than F1. So what happens if R naught equal to S1 is equal to S1? So if R naught is equal to S1, then C R naught is equal to C prime R naught equal to 0, because R naught psi R naught is now, we assume that R naught equal to S1. Okay. And by lemma, psi double prime R naught is negative. So in this case, we have psi should be this. Okay. So in this case, we only have one root. But before, we showed that psi has at least two roots. So this is impossible. So we can say that there exists one solution, unique solution between here, and there is a unique solution between here. And on the other side, we said that Yes, we said that psi has two roots here, between here. So we can conclude that psi has exactly two roots between 0 and 1 for each k. So in such a way, we can prove the existence of the surface for each k, for each genus. Okay. So, and in this setting, when k equal 1 case, Professor Lopez and I could prove the existence, uniqueness of the surface under the assumption of certain symmetry. But in this case, we can observe that symmetry group of this surface. But so far, the uniqueness is not proved. But maybe we can do something similar way. We can prove the uniqueness. So I hope somebody here can do the proof. Okay. And so the difference is the first paper is no orientable surface, which we constructed maybe strip and the crime bot, one-ended crime botter, and we proved the degree of the Gauss map is always even. And the next paper, we generalized the genus, higher genus case. And the third paper, my student Kaneda, he did, he proved the two-ended projective plane, and the uniqueness is proved there. So he got PhD with these papers recently. Okay, so I stop here. Thank you very much.